Welcome to Complex Analysis Lesson 20. This lesson is on classification of poles, or sometimes known as roots, classification of singularities. We'll see several theorems related to this topic, and we'll also provide some examples. And at the very end of the lesson, we're going to talk about Picard's little theorem and Picard's great theorem, which are kind of surprising results, and we'll get to those, as I say, towards the end of the lecture. We can use the various series expansions of a function to study the behavior of the function at points called zeros and also at isolated singularities. So recall from before, 0 is just the point where the function equals 0. And an isolated singularity is a point where the function is analytic around the singularity, at all points around the singularity, but at the singularity itself, it's not analytic. So we have an example here of sine z over z. At the point z equals 0, we have this isolated singularity where the function is not defined, but anywhere outside of the point 0, we do have a defined function. So this z equals 0 is an isolated singularity for this particular function. And it also has zeros at plus or minus an integer times pi, and that's because sine equals 0 at those points, and of course z is not 0 at those points, so the function is well defined there. When we talked about polynomials in a previous lesson, and even from basic algebra, we know that when we have roots of a polynomial, we can write them we can factor them out in the form of x minus whatever the root is. So x minus 3, it could be factored out of a polynomial. And if the root is repeated, then we have something like x minus 3 to the 4th power times whatever's left in the polynomial, and that would be a root of order 4 in that case. What we're going to talk about here is a little bit more general classification of roots of order n, not just for polynomials, but for any complex function. So here's how we're going to do it. Consider a function f that is analytic in a domain D containing a point z sub 0, and what's this condition here, that f of z sub 0 equals the derivative of f of z sub 0 equals the second derivative evaluated at z sub 0 all the way up to the n minus 1 derivative evaluated at z sub 0. They all equal 0, but the nth derivative evaluated at z sub 0 does not equal 0. Then f is said to have a 0 of order n at z sub 0. In this case, the Taylor series around z sub 0 has this form here. So we know that the first n minus 1 terms here all are equal to 0 because of the condition that we're given here on the derivatives, and just using the formula for a sub n going from 0 to n minus 1. These all drop out, and so you have this format for f of z under this condition here. And of course we can factor out of z minus z sub 0 to the n, and then what's left is some function g of z, where g of z looks like this here. And the function g of z converges wherever the series for f of z converges, since for any given point the functions are just a constant multiple of each other. So g of z is analytic in a domain D about g sub 0, and g of z sub 0 doesn't equal 0. That's from our condition up here. So we have this a sub n cannot be 0, otherwise the nth derivative of it evaluated at z sub 0 would equal 0, and that would contradict our assumption. So we have that g sub 0 does not equal 0. The converse of the theorem we proved in the previous slide is true. So if f of z is of this form here, z minus z sub 0 to the nth power times g of z, where g of z sub 0 does not equal 0, then f must have a 0 of order n at z sub 0. And the reason for this, I didn't write out all the details, but I'll just explain it in words. If you take the first all the way up to the n minus 1 derivative of f, each term in the derivative is going to have a z minus z sub 0. So when you evaluate f at the derivative of the various derivatives of f at z sub 0 up to n minus 1 derivative, you get 0. When you do the nth derivative, there's going to be a separate term that has a g of z in it with nothing else, and that won't evaluate to 0, and that's basically gives us the definition of a 0 of order n. So I just wrote this here in terms of a theorem. If f is analytic in a domain about a point z sub 0, f has a 0 of order n if and only if this condition f of z is of this form, z minus z sub 0 n to the nth power times g of z, where g of z is analytic in the said domain and g of z sub 0 doesn't equal 0. So we can verify this theorem or convince ourselves that it works for a couple of examples here. And I took one example, f of z equals z minus I cubed times z minus 5. And if we look at this at the root I, we can see that it's of order 3. We know it from the theorem, but we're going to show it via the definition. So we take the first derivative and we get z minus I cubed times the derivative of z minus 5, which is 1. Then the derivative of the first is 3 z minus I squared times the second. And when we plug in I, we just get 0 because both of these terms go to 0. Then we take the second derivative. It gets kind of long here, but you take this here and you get 3 z minus I squared. Then the derivative of this product is 3 z minus I squared times derivative of z minus 5, which is 1. Then the derivative of this, 6 minus z minus I times z minus 5. And these first two terms add together, you get 6 z minus I squared. And then this term carries over. And you notice again we have a z minus I in both terms. So when you evaluate the second derivative at I, you get 0. Take the third derivative and you get 12 z minus I. Then this is the derivative of this product is 6 z minus I plus 6 z minus 5 using the product rule. These first two terms add to 18 z minus I, then 6 z minus 5. So when you put in I now, this term goes away, but this term, this is like your g of z. This term here, it does not equal 0. It equals 6 times I minus 5. So we have established through the definition of a 0 of order 3 in this case that this function f of z has a root I of order 3. Here's another one, another example. We take f of z equals z plus 1 squared times e to the z. Take the derivative here using the product rule. We get this expression. We put in minus 1, and again both terms have a z plus 1 in it, so that evaluates to 0. We take another derivative and we get this rather long expression here. You get you need the product rule twice for this term and then for this term. You get all this here, and these three terms have the same factor z plus 1. So when you put in minus 1 here these cancel, but then this last term evaluates to 2e to the minus 1, and that doesn't equal 0. Now in this case, unlike the previous case, all future derivatives are going to have this term in it, this 2e to the z, and so none of the future terms are going to evaluate to 0. They'll all be non-zero. I guess that's not important in terms of our theorem, but I just thought I'd mention that here. And in this case here, for the first example, the fourth derivative will not equal 0, but then the fifth and onward will all evaluate to 0. But again, that's not critical to the theorem at point. Okay, let's continue. The zeros of non-constant analytic functions are isolated, and we're going to prove that in this theorem here. So if f of z sub 0 equals 0 and f is analytic in the disk about z sub 0, then either f is identically 0 in the disk about z sub 0, or there is a punctured disk about z sub 0 in which f has no zeros. So let's prove this. If f is analytic, then we have by theorem 137 from the previous lesson that there's a Taylor series representation given by this representation here within some disk about a z sub 0. We have two cases. If all the a sub n's equals 0, then of course f of z equals 0, and that's the first possibility in our theorem. If not all the a sub n's are equal to 0, then there's some k greater than 1, greater than or equal to 1, is the smallest subscript such that a sub k doesn't equal 0. And then by definition, f of z has a 0 of order k at z sub 0. Now what we want to show here is that there's a punctured disk where f of z doesn't, about z sub 0, where f of z doesn't have any zeros, which is, to me at least, kind of interesting that has to be the case, but it is. So by theorem 141, that was from the previous slide, f of z can be represented in this form, z minus z sub 0 to the k power times g of z, where g evaluated at z sub 0 does not equal 0. Then also by theorem 141, g of z is analytic and thus also continuous at z sub 0. So there's some disk, by the continuity really, there's some disk about z sub 0 less than some radius r over which g is non-zero. And so f is also non-zero in a punctured disk about z sub 0 because f is just the product of g of z, and then which isn't 0, and then z minus z sub 0 is also continuous and not equal to 0 in some punctured disk about z sub 0. And so we have a proof of our theorem. So let's look at a couple of examples, or actually counterexamples. If f is non-constant analytic and equal to 0 at z equals 0, the order of the 0 must be a positive integer. We saw that from the previous theorems. But if f is not analytic, the order of the 0 is not necessarily an integer. For z to the 1/2 power, we actually define the 0 at z equals 0 as being of order 1/2. And in the case of the modulus of z, there is a 0 at z equals 0, but it's not even, the order is not defined at all. Then looking at isolated singularities, we have an example here, the tangent of pi z over 2. Recall the tangent of z is just the sine of z divided by the cosine of z, and the cosine of z equals 0 at pi over 2, minus pi over 2, 3 pi over 2. So every pi over 2 plus or minus pi. And so you get isolated singularities at each odd integer value of z for the tangent of pi z over 2. So let's classify the isolated singularities. We're going to use the Laurent expansion of a function at about z sub 0. And I wrote it down here just to remind us what it looks like in general. There's three cases depending on whether or not or how many of these c sub n's are not 0 when the index is minus. So if the c sub n equals 0 for all negative indices, then we have what's called a removable singularity, and the Laurent expansion just becomes a Taylor series. It looks like this, and our a sub 0 can be used as to define the function at f of z sub 0. So we know that f of z sub 0 doesn't exist because we assumed it was an essential singularity, but the limit does exist. And in fact, it equals a sub 0. So we can redefine the function at z sub 0 to equal a sub 0 and effectively remove this singularity. So I'll show you an example of this, and hopefully it'll be a little clearer when you see what I mean by a removable singularity. Now, a simple pole is the case where you do have some non-zero coefficients here with negative indices. And if the largest one is k, so say you have c minus 10 not equal to 0, and everything after that, c minus 11, 12, they're all equal to 0, then you have a pole of order k by definition. And if k equals 1, it's called a simple pole. And then the last case is when all the, or should I say an infinite number of the coefficients with negative indices does not equal 0. So it doesn't have to be all, but an infinite number of coefficients with negative indices equals 0, do not equal 0. Then you have what's called an essential singularity, and that's equivalent to the neither the limit as z approaches 0 of f of z, nor the limit as z approaches 0 1 over f of z existing. And we'll see some examples, and hopefully that'll make this a little bit easier to understand. Okay, some examples. So we saw this function before, sine z over z, that has a singularity at z equals 0. This blows up there, so the function is not defined. And if we expand sine z in terms of the Taylor series, and that, or I guess Maclaurin is the proper term, and then multiply by 1 over z, we get this expansion. And then we can say, well, the limit as z approaches 0 actually equals 1, and we can redefine f of z at 0 to be 1, in which case we effectively remove the singularity, which is why it's called a removable singularity. Okay, and we have another one here. F of z equals e to the z minus 1 over z, and again, this blows up at z, but if we write e to the z minus 1, so this is e to the z, the Maclaurin series, and then minus 1, we get this. And then again, we could do the same thing, f of 0, or should I say the limit as z approaches 0 of f of z does equal 1, and then we can redefine f of 0 to be 1, in which case we remove the singularity. All right, some more examples. F of z equals z squared over minus 4 over z minus 2. When z equals 2, this is undefined, but we can factor the top and the bottom. So the z minus 2 cancels with the z minus 2 in the numerator, and that leaves us with z plus 2. So the limit of this as z approaches 2 equals 4. And again, we can remove the singularity by redefining f at 2 to be 4. All right, the next one is not a removable singularity. Let's just write this out. So we have z, e to the z minus 1 divided by z to the 4th. And clearly it has a singularity at z equals 0. We write e to the z minus 1 here in the brackets, square brackets, multiply by 1 over z to the 4th. And you see here we do get some terms in the Laurent expansion that are non-zero. The biggest one is here, was basically coefficient c minus 3. So this is, and everything beyond that is equal to 0, the coefficients. And so the singularity is a pole of order 3. And here we have an essential singularity. So f of z equals e to the 1 over z has a singularity at 0. We can see that because the function blows up, it's undefined there. But if we do the Laurent expansion, and we did this before, but I'm just repeating it here. So we plug in 1 over z for the Taylor series for e to the z, and we get this here. And you notice that we have an infinite number of terms with negative coefficients. And so that, by definition, is an essential singularity. And you can, if you want some exercises to try, you can go back and from the previous lecture when we did the sine of z and cosine of z and plug in 1 over z in each case, and you'll get something like this. And then you can conclude again that they're essential singularities. Okay, we have a theorem here concerning removable singularities. If a function f has a removable singularity at z sub 0, then these three things are true. Let me start with 2 and 3 since we already know this. F of z has a finite limit, and as z approaches z sub 0, and whatever that limit happens to be, let's say it's L, then we can redefine, or define, I should say, f of z sub 0 to equal L, thereby removing the singularity. The one thing we didn't see was this property here. F is bounded in some punctured disk about z sub 0. And then we have a converse, or sort of a converse here. If a function f is bounded in some punctured disk about an isolated singularity, z sub 0, then the singularity is removable. So that's kind of interesting. Function is bounded, so it's less than some number, say 50. The modulus of f is less than some number in some punctured disk about the isolated singularity, then the singularity is necessarily removable. It's quite interesting. So I'm not going to prove this here, but I'll refer you to Lemma 5 in section 5.6 of the book by Saff and Snyder, which I've referenced a few times already. Okay, we have two theorems here, both named after Picard, and one is called Picard's little theorem. It says if a function f is entire, remember that means analytic over the entire complex plane, and non-constant, then the set of values assumed by f is either the whole complex plane or the plane minus a single point. That's rather surprising. You might not expect it. So if the function doesn't equal a constant value like 1 plus I all the time, and it varies, and it's analytic in the entire complex plane, then either it takes on every possible value over the every possible complex number as a value, or it takes on every possible value minus a single point. And I mentioned here the single point exception is needed in the above theorem. For example, e to the z is entire and non-constant, but it never takes on the value 0. So that's why we need this exception here to the theorem. Then there's Picard's great theorem. If an analytic function f has an essential singularity at a point z sub 0, then on any punctured disk about z sub 0, f takes on all possible complex values with at most a single exception, not just once, but infinitely often. So that's, again, a bit surprising. That means the function just varies wildly as you get near an essential singularity. Again, I'm not going to prove this, but if you go to the Wikipedia article and just look up Picard's theorem, you'll see proofs of both of these. They're not particularly simple proofs, but again, if you're interested, you can find them at this location. So on this slide, we are going to talk about equivalent conditions for each type of isolated singularity. We have this theorem here. Just as a reminder, this theorem numbering is coming from my book, which I've made freely available. I mentioned this in the introductory video, and I also gave a link to my book. And so that's why these numbers are kind of large, because it's actually coming from the third chapter of my book. And so there's a bunch of theorems that come before this. So in any event, z sub 0 is a removable singularity if and only if the modulus of f of z is bounded in some punctured neighborhood about z sub 0, and that's true if and only if the limit as z approaches z sub 0 of f of z exists, and that's true if and only if f can be redefined to be analytic at z sub 0. So these are useful in the sense that sometimes it's easier to apply one of these equivalent conditions than the actual definition. And that's true for the next two items that we're going to talk about. The second one is a pole. Z sub 0 is a pole of order m. M is a positive integer. If and only if the limit as z approaches z sub 0 of the modulus of f of z equals infinity. And that's true if and only if f of z can be written in this form here, g of z divided by z minus z sub 0 to the m in some punctured neighborhood of z sub 0, where g of z is an analytic function such that g of evaluated at z sub 0 does not equal 0. And then we have these equivalent conditions for an essential singularity if and only if the modulus of f of z is neither bounded in any neighborhood of z sub 0 nor goes to infinity as z approaches z sub 0, and that's equivalent to f of z assumes every complex number in every neighborhood of z sub 0 with one possible exception. So that's kind of a reference back to Picard's theorem from the previous slide. And if you're looking for a proof, I'll again reference the Safin-Snyder book. This is in section 5.6 of that book. So that's the last slide in this lesson. I have a few more lessons that I'll be putting up for your listening pleasure, and thanks for following along.